In a previous video, we saw this theorem that the monotonic function with domain AB has at most a countable number of discontinuities. We already saw the proof. Here, I just want to make a remark and emphasize a point. See, this is the remark that given a countable set E in the domain, which could be even dense, we can construct a function f that is monotonic in AB, which is discontinuous at every point of E and continuous otherwise. So what this remark is saying is that no matter how wild the set of discontinuities is, there will always be a function that is discontinuous there, okay, as long as the set is countable, okay, the set E. In other words, you can pick a set E that is completely crazy, but countable, and I will be able to find a monotonic function that has discontinuities only at the points in E. Here, I'm emphasizing that E could be dense because when we picture a countable number of discontinuities, what we have in mind is a function that has a few jumps and that's it, okay? But that's not what we are saying here. A dense set A being dense in X means that the closure of A is equal to X. So that means that a set of discontinuities that is dense in AB would be spread all over. Okay, it would be like the rational numbers, for example. The rational numbers intersection with AB is dense in AB. Okay, and those are spread all over. So you cannot really, then it becomes very difficult you cannot graph a function like that. It becomes very difficult because the set of discontinuities is intertwined with the set of points where the function is continuous. Okay, so, but let's give an example. So to give an example of this type of function, let's call it proof, even if it's not exactly, well, no. Let's just go ahead and do it. Here, because E is countable, we can exploit this fact and assume that it's arranged as a sequence. Okay, so we have, we can write E as the sequence xn, n equals 1, 2, and so on. This is a sequence that sweeps the whole set E. Now, once we write this sequence, the way we are going to construct the function is taking a series with the coefficients Cn that are non-negative, okay? And such that, well, it converges. So let's say take a convergent series. Okay, so from 1 to infinity. So this is all we need. We have a convergent sequence and the set E that is arranged. Sorry, I said a convergent sequence, I meant a convergent series. With these two, we can construct our function just defining f of x as the sum of the Cn for those indices n such that xn is less than x. So let me explain this a little better. What does this summation here mean? Of course, this x is in between a and b. That is the domain. So here what we are saying is that the sum is taken over those indices n for which xn in the sequence that sweeps E is less than x. If there are no points xn to the left of x, then this sum is empty, and as we usually do, then that sum would be 0. Okay, so in that case, f of x would be 0. Now, you could argue, what happens if we rearrange this series? No problem. It's a series of positive terms, so it converges absolutely. So the series converges absolutely. So, so the order in which we arrange the terms doesn't matter. Okay. Now, again, just one last time. So the way this is working, so we have our AB here, and we have the sequence that is sweeping through our set E, and then we have some number x, let's say here. Okay, and what we are going to do is we are going to be following the sequence, okay, for as long as the terms in the sequence are less than x. If they are less than x, then we add the corresponding coefficient Cn. So it will be the first, C1 plus C2 plus C3 plus C4. C5 is here, we don't add it. C6, 7, we don't add it. 8, 9, 10, 11, 12. So if it falls on the right of x, it doesn't get added. If it falls on the left, then it gets added. Okay, that's the way we are defining it. And this function here, it looks very very strange, but actually it has good properties. F turns out to be monotone increasing on AB. Okay, that's the first property, and this one actually it's, let me copy the definition. This one actually is it's easier to prove, okay? If we want to prove that f is monotone, we need to show that if x is less than y, then f of x less than f of y. But notice what happens here. This is the sum that corresponds to fx here. Can we compare it with the sum that corresponds to fy, which is this one? Yes. Because x is smaller than y, that means that in this second sum, we have at least as many terms as in the other sum. So this sum has at least as many terms as the other one. Okay, so then we have less or equal, but that is the definition of monotone increasing, that x less than y implies f of x less or equal than f of y. All right, so that gives the first interesting property of this function. The second one is that f is discontinuous for all x in AB, sorry, not in AB, in E, and continuous otherwise. This is not so easy to see from the definition. Okay, this is our definition of f of x. Not so obvious. Oh. So let's see, how do we prove that this is discontinuous for points in E and continuous otherwise? It's actually also not that difficult. What we are going to show is that we are going to study what happens with fx minus and fx plus, okay? If they are equal, and they are equal to f of x, then f continues. If they are different, then f is discontinuous. That's the strategy. That's what we are going to see. So we'll use, so let's see. First things first, let's write down carefully what is fx minus and fx plus. So fx minus is the limit from the left of f of x. So we can write limit of f of s as s tends to x from the left, but we are going to write it in a slightly different way. We are going to write it x tends to x growing from the left, okay? You notice that I used an upwards arrow instead of an arrow pointing to the right. This is a notation that it's used sometimes. Here I find it particularly useful. Okay, I'm going to keep this in a parenthesis just so that we know what this means. Okay, but in this particular case, then we have the limit as x goes up to x, sum of the Cn xn less than x. Here, what we mean with this limit, notice that we are taking xm less than s, okay? So our xm are over here, and somewhere here there is a, okay? But these s, they are growing all the way to some limit x. So is this value x included in the limit or not? Notice that these sets are bigger and bigger and bigger, but they are always open on the right, okay? So the limit here is going to be the sum of the Cm when xm is less than x, strictly less, because we are always leaving x out. Okay. But what is this? This is the definition of f of x. Isn't this nice? So we have shown that the limit from the left is always equal to f of x. Okay, when I mean always, I mean for every x in the domain. Just as a side note, this means this is called left continuity. Okay, this is, well, here we say that f is continuous at x from the left. Okay. There is an analogous definition of continuity from the right. Okay, that case would be f of x equal f of x plus. But this is an important piece of information. Now, we have studied f of x minus. Let's do f of x plus. Okay, in this case, we have the limit as, let's call it t goes down to x. That means t to x plus from the right of f of t. And this is the limit as t goes down to x of the sum of xm less than t and then cm. Okay, but now what happens? So now it's a bit of the opposite situation. Here we have a, here we have x, and we have our xm over here, but then our t here, they are going to go from right to left. And you see what happens? X is always contained in these sets, so it will also be in the limit. So this is the sum xm less or equal than x cm. Oh, so this looks very similar to the definition, except that we have less or equal. So how to handle that? Well, let's go one thing at a time. Here, it depends if x is in E or not. Okay, so here we have two cases, x not in E or x in E. If x is not in E, then it doesn't matter because fx plus equals the sum xm less or equal than x cm. And here notice what happens. Because x is not in E, then by reaching all the way to x, no cm is going to be added. Okay, so we are adding exactly the same number of coefficients cm, whether we include x or not. But if x is in E, then it's different because when we reach to all the way to x, we will be adding one more coefficient than if we don't. Okay, in this case, we can take x equal xn, okay, because of the way we wrote E as a sequence. Okay, so in this case, we could write fxn plus, which is the sum of cm xm less or equal than xn. This is the reason why I wanted to keep the end free and used cm and xm before. Okay, but now, in this case, it does make a difference to reach all the way to xn, okay, because then we are adding one more coefficient. So we can write this down as xm less than xn cm plus cn. Just single out the last coefficient. But this here is f of xn. Okay, and this is all we need. By the way, here I didn't really finish, right? Because I said fx plus, but it's equal to the sum leaving out x, but then I should have said, yeah, but that is f of x. So let's collect all the information we got. So we got for all x in AB, f of x minus equals f of x. If x is in E, f of x plus equals f of x. If x is not in E, that is x equals xn, the other way around, sorry about that. If x is in E, that is if it's some element of the sequence, fxn plus equals f of xn plus cn. All right, so let's call this 1, 2, and 3. So 1 and 2 mean that f is continuous for every x not in E. Okay, because we are saying that the lateral limits are both equal to the value of the function at the point. And then 2 and 3 are saying that f is discontinuous for every x in E. Okay, because, well, it's kind of obvious, right? So we are saying here f of xn would be equal to f of xn plus, not 2 and 3, I meant 1 and 3. Now it's correct. So fxn minus equals fxn. Okay, and then we know that fxn plus equals f of xn plus cn. Therefore, the difference equals cn. And this will, and this is positive. Okay, so here I need to go back one moment to correct a minor thing. Here, when I said that the cn would be non-negative, I should have said that they are positive. Okay, you see, because otherwise here, when we arrive to the end, we will have only for some points that there is a discontinuity. Okay, so that's something to keep in mind. But here we are saying that the lateral limits are different. There is a jump, and the jump is given by Cn.